Well, hello. Now we're going to do the Chapter 5 Review Questions and Problems. I'm on page 174. We're going to go over the review questions just real quickly, then move on from there to the practice problems. Number 1, state Newton's three laws in your own words. You will be required to memorize these for the test. I think there's a question that says you have to write these down. So real quickly, Newton's third laws. The first law is that an object in motion will remain at motion or at rest or remain at rest unless acted upon by an outside force. Law number 2 is really F equal ma, that the summation of the forces is equal to the mass times the acceleration of that mass. And law number 3, for every action or force, there is an opposite and equal reaction force. Question number 2, why will friction always be present when two surfaces touch each other? Friction will always be present because when two surfaces touch each other, there's really jagged edges of contact that will grab to each other. Down at the micro level, at the molecular level, these surfaces will contact each other, and a force must be applied. These two surfaces will grab each other, and a force must be applied to actually pull them apart. Okay, question number 3. A man is riding on a horse at a quick gallop. Suddenly the horse stops. When this happens, the rider flies out of the saddle and lands on the ground. Does the rider fly forward or back? He flies forward over the horse's head. And what Newton's law is used to explain this is the first law. The rider is in motion. He's going in a certain velocity. The horse stops, and when the horse stops, the rider just keeps on going. And so that's an application of Newton's first law. Question number 4, a student applies the same force to two objects. If the first force is 1,000 times more massive, 1,000 times more than the second, which accelerates, the first mass is 1,000 times more massive than the second, which accelerates more quickly. Well, he applies the same force to both of them, but the first one is 1,000 times more massive, and so the first acceleration will be 1,000 times more slower than the second acceleration. Okay. Number 5, which of the following are real forces of units of force? Pounds that's pounds of force. A slug, no, because that is a unit of mass for an English unit. Kilogram times meter divided by second, no, that's not a unit of force. Slug times mile divided by hour squared, well, those are some crazy units, but yes, that is a unit of force because the unit of force is mass times acceleration, and that, the last one is. Question 6, a physics student writes down an object, he writes down the value of 13.1 newtons. Is that a mass or a weight? That's his weight. That's a force, so it's its weight. Okay, question number 7. Physicist uses the same scale to measure the mass at two different locations, Death Valley and Mount Everest. Is the measurement accurate in both locations? Well, it should be. Yes, but let me rephrase the question a little bit. Will he get the same number? No, he won't get the same number. That is the same weight. Not likely, because I'm pretty sure that the acceleration of gravity at Death Valley is different from the acceleration of gravity at Mount Everest. The acceleration of gravity, and we'll talk more about this in 2 chapters, I think, but the acceleration of gravity is dependent upon the elevation, where you are in the elevation of the Earth. What's your elevation? because that defines the distance to the center of the Earth. But it also depends on the local geology, basically. If you have real dense rock that's under you, then your acceleration will be more. So it depends on several factors. Question number 8. What is the normal force? The normal force is the force that's perpendicular to a surface. If this is the normal force, if I have an object that's sitting right here on this surface, the weight acts down. The normal force is the force of the surface acting up on the object. And it's important because the normal force is used in the calculation of friction. Number 9, a physics student is measuring friction coefficient. So on one surface he measures a coefficient but neglects to write down, is it static or is it kinetic? And he writes down 0.23 and 0.54. So which is it? Well, we always know that the static coefficient is greater than the kinetic for a given surface. So the static must be 0.54 and the kinetic coefficient of friction must be 0.23. Number 10, when a tire rolls on a road that pushes against the road, according to Newton's third law, what must happen in response to this push? Okay, the tire pushes against the road pushes against the tire. That's Newton's third law. In fact, for the car to move forward, in fact, if you think about this, for the car to move forward, or for us to even walk on a surface, there has to be friction. If there weren't friction, we would not be able to apply a force in the opposite direction. If we had a perfectly smooth surface, when you went to apply a force in a certain direction, how do you do that when you walk? You have to lean. If you leaned over on a slippery surface, you've done that before, what happens? You tend to fall. So actually, friction is actually a good thing when it comes to surfaces because it allows us to actually propel ourselves forward. So at this point, I'm going to switch over to page 175 and page 176, and we're going to go over some of these practice problems. Not sure we'll do all of them, but we'll see. Okay, number 1. A father is teaching his young daughter to ice skate by pulling her across the ice on a short rope. If the daughter, so here's the daughter on skates, and he pulls her on a rope. And the mass of the daughter is 25 kilograms. Let's see, and she starts to accelerate at 0.35 meters per second squared. The question is, what is the force that the father is pulling her with the rope? Well, that's just a straight application of Newton's second law, F equal ma. So if the mass is 25 kilograms and the acceleration is 0.35 meters per second squared, that must mean that the force that he was pulling with is 25 times 0.35, or 8.75 newtons, which would round up to two significant figures, 8.8 newtons. Okay? Okay, question 2. A 501-pound rock has fallen onto a frozen pond that you want to use as an ice skating rink. You push the rock So here's the rock. The rock weighs, the weight of the rock is 501 pounds. That's the weight, not the mass. Okay. Now, if you push the rock with a force of 16 pounds, how fast will it accelerate? And we want to assume that there's no friction, so basically we're assuming that the static coefficient and the kinetic coefficient are 0. No friction. The question is, how fast will it accelerate? Okay? Well, we know that F equals ma. Do we know the mass? Well, we kind of know the mass. We know the weight. We know that the weight is equal to the mass times gravity, right? Right here. So, we can solve for the mass. The mass must be equal to the weight divided by the gravity. So we have 501 pounds. LBS is an abbreviation for pounds, divided by 32. You have to use English units here, feet per second squared. That gives us a mass equal to 501 divided by 32 of, let's see, I'll round it off to 3 significant figures, 15.7 slugs, because that's an English unit of mass. 15.7 slugs. 501 divided by... Okay, that's the mass. So to find out that's step 1. Step 2 is to use F equal ma, Newton's second law. We know what the force is. Now we know what the mass is, we can solve for the acceleration. Force divided by mass is the acceleration, which is 16 pounds divided by 15.7 slugs. 16 divided by 15.7 is 1.02, let's say, which actually we should round off to 2 significant figures, 1.0, and this will be feet per second squared, because we're in English units here. So in this case, we can solve the acceleration. We were given the mass, we were given the weight, but we can solve for the mass. Okay, question 3 is, going back to question 2, I asked you to assume that there is no friction between the rock and the ice. You do, however, have to assume that there is friction between your feet or whatever is on them and the ice. Why? Well, okay, so this kind of goes back to what we were talking about back at the review question number 10. If there were no, here, let's draw a picture. We have a mass here. The weight acts down. The weight acts down. So we know that the normal force acts up. The normal force acts up. Okay. Think of the point of view of a, let's see. Think of a person walking. Here you're how's that for a person walking? Here's a person walking. His weight acts down. Okay. he wants to move forward. So in order to move forward, what do you have to do? You have to lean forward. When you lean forward, you're applying, when there is a friction acting back this way, he's moving, you're moving this way, but there's a friction force that acts back. Okay? There's a friction force that acts back. You have to apply a force acting this way. Okay? You have to apply a force acting this way. But notice that the sum of these, you have the weight acting down. The friction acts this way on, here's your foot. The friction acts this way. The sum of these is actually a vector. We'll call it, well, I won't call it anything. It's just a sum of the weight and the friction acting back. You have the normal force acting up on the road. Okay. You have to apply a force this way in order to accelerate that's greater than the friction. And notice that you have to, the force, the total force is you have to lean, it's a force that acts at an angle to the vertical. You have to lean. You have to lean into it. You have to lean forward actually to walk. Have you noticed that? You have to lean forward to walk, and that's because you have to counter the friction. If there were no friction, then this force would not be here, this back force would not be here. You would not be able to produce, if you would not be able to produce this force forward, because if you tried to, you would fall flat on your face. So the fact that we can walk is a testament to the fact that there's friction. Good thing the good Lord put it there, otherwise we wouldn't be able to walk. Kind of a long-winded answer. Sorry about that. All right. Question number 4. A rock has a mass of 200 and the mass of a rock is 523 grams. What is the weight? Well, the weight is simply the mass times acceleration of gravity. Let's convert this into kilograms. 1 kilogram is equal to 1,000 grams. Grams cancel out, so the mass is equal to 0.523 kilograms. So we take the weight is 0.523 kilograms multiplied by 9.8 meters per second squared, and we get the weight which is 5.1, rounded off to 2 significant figures, kilogram meter per second squared, which is a Newton. So that would be the weight. Okay, number 5. A box of cargo bound for space exploration weighs 1,234 pounds on Earth. What will be the weight on the Moon? The acceleration of gravity on the Moon is 5.3 feet per second squared. Okay, this is a good question. The mass is, well, excuse me, no, we don't know the mass, we know the weight. The weight on Earth, I'm going to put Earth weight, is 1,234 pounds. Okay. Now, remember, on Earth, this is equal to the mass times the gravity on Earth. I'm going to put Earth gravity. and Earth gravity is 9.8. We know what that is. Now, the weight on let's see, what is it? The weight on the moon. The weight on the moon, whatever it is, it's equal to the mass, the same mass, times the gravity of the moon. Whoops. Times the gravity of the moon. The gravity of the moon is 5.3 meters per second squared. The gravity on the Earth is of course 9.8 meters per second squared. Do I have that number right? 5.3? Yes, it's 5.3. So, we have two equations, and the link between these two equations is the mass. The mass is the same for both the Earth. The mass hasn't changed. If we take the mass to the moon, the mass is still the mass, but the gravity is different. So, notice we can take the first equation and say that the weight of the Earth over g of the Earth equals the mass. And we can also say that the mass is equal to, second equation, the weight on the moon divided by the gravity of the moon. Notice here I set up a ratio. I can do that. The mass is the same in both cases, but over here we have the weight of the Earth divided by the gravity of the Earth is also equal to the weight of the moon divided by the gravity of the moon. So I can really set up a ratio. What we want to solve for is the weight on the moon. That's what we don't know. So what we don't know is the weight on the moon. So let's solve for this. The weight on the moon equals the weight on Earth times the ratio gravity on the moon divided by the gravity on the Earth. Okay. Notice, so I'm solving this problem. I could have gone ahead and just solved for the moon, for the mass. I could use the first equation to solve for the mass, and then calculate put the mass in here and solve for the weight. But actually, I don't even really have to solve for the mass, because I can use this ratio, and I'm just applying the ratio of gravity on the moon to the gravity of the Earth. Anyway, so what do I end up with? So using this ratio, I come up, here's the weight, I'm going to put over here, the weight 1,234 pounds, I'll abbreviate it, times the ratio of the gravities. We have 5.3 divided by 9.8, and they're both in the same units. Meters per second squared, meters per second squared. It's really the ratio that's important. So we have 1,234 pounds times 5.3 divided by 9.8, and we end up with 667 pounds. 667 pounds, which we could round off to two significant figures if we care to. Okay. So that was question number 5. Okay, question number 6. An astronaut weighs number 6. An astronaut weighs 296 newtons on Mercury, where the acceleration is 3.98 meters per second squared. How much does she weigh on Earth? This is the very same kind of situation. So the astronaut weighs, the weight is 296 newtons. That's the mass times the acceleration of gravity on Mercury. I'll go gravity of Mercury. That's the weight of mercury. And we know that this is, they say, is 3.95 meters per second squared. The question is, how much does she weigh on Earth? The weight on Earth is question mark, and of course that's Earth, the gravity of Earth. This is the exact same kind of question, so all I'm going to do is just I'm not going to solve it, I'm just going to set you up for it really. What's the same? The mass is the same in both situations, so we can set up a ratio. The weight on Mercury divided by the gravity on Mercury is equal to the mass, and that's equal to the weight on Earth divided by the gravity of Earth. Okay, and so we're solving, what we want to solve for is this, the weight on Earth. And so the weight on Earth is simply the weight on Mercury times gravity on Earth divided by the gravity on Mercury. Just like the other problem, we just plug in the numbers and we should get the answer. Okay? Okay, on to question number 7. Okay, number 7. A box with a mass of 745 kilograms is sliding along a floor, is sliding across the floor. And it says that the static coefficient of friction is 0.45. The kinetic coefficient of friction is 0.32. So it says that it is sliding, so that means it already has some velocity. It's moving, so it has some velocity. We'll just call velocity V. It says, what is the frictional force between the box and the floor? Okay, what is the force of friction? Well, if the box is moving, do we use the static or the kinetic? We use the kinetic. The box is moving. So even though they give you the static coefficient, we don't really use it. They just gave it to you to make you think. So we're going to be using the kinetic coefficient of friction of 0.32, which I'll place over here. Okay, so how do we calculate friction? It's a two-step process. First, again, we look at the sum of the forces in the y direction. We have the weight acting down and the normal force acting up. Okay, so the weight, which acts down, is opposite the normal force, which acts up. And we know that that's equal to 0 because the box only the box only moves horizontally. It does not accelerate vertically at all. So this is equal to 0. So that of course means that the normal force is equal to the weight, which equal to is mass times acceleration of gravity. Okay? So that gives us the normal force. In the next part, we do the sum of the forces in the x direction. Okay, sum of the forces in the x direction. And well, is there a force that's pushing on it this way? We don't know. We actually don't know. The only thing we know is that the mass is moving. So actually, we assume not. So there's only one force acting on this, and it's the friction force. So the force of friction, there's only one force acting on this. the force of friction, and it's actually acting that way. It's acting backwards. We'll just put the r that way. And it's equals to the mass times acceleration. Okay. Well, what is the force of friction? The force of friction is the kinetic coefficient times the normal force. Okay. So, and actually the question said just what is the frictional force. It doesn't say what's the acceleration, but we could calculate that also. So the frictional force, I'm going to erase this right here. Actually, the force of friction, just to answer the question, equals the kinetic coefficient times the mass times gravity. The size of that will be 0.32 times the mass, 745 kilograms, times 9.8 meters per second squared, which gives the frictional force 0.32 times 745 kilograms times 9.8 is 2,336. We have two significant figures, so we should really round this off to